So let's take our first example. So let's say that we are given a recursive algorithm, and this equation basically represents a particular type of recurrence. So Tn is equals to 9 Tn divided by 3 plus n. In this section, we are going to just solve this equation and we are going to analyze these cases. In the next section of this video, we are going to see how are we getting this equation. So for example, we are going to pick up the merge sort algorithm, which is a recursive algorithm, and then we are going to obtain this equation and we are going to see how we can obtain this. And then we are going to follow the same steps as we are following in this particular example. So let's say you are given a runtime of a recursive algorithm like this. So what you will have to do is simply you will have to compare this whole equation. So let me put a box here. So if you're given this equation, you will have to compare this with this equation. So let me mark this equation as 1 and let me mark this equation as 2. So you will have to compare 1 and 2. And you can see by comparison, you will get the value of A is equals to 9. And the value of B is equals to 3. And the function is equals to n. So when you have got these value, applying master theorem becomes very easy. What you will have to do is, in step 1, you will have to find out the value of n raised to the power log base ba. So you can see that n log b is 3, so base 3, and a is 9. So this gives us a value of, so if we apply logarithm on this, you will basically get the value of n squared. So for this master theorem, you will have to know the basics of the logarithms in mathematics. Then only you will be able to solve this term. So log base 9 is 2, because if you want to write 3 square is equals to 9, and if you can write this as log base 9 equals to 2. So this is one and the same thing. So I've used this concept in here. So log base 9 represents 2. So the value, the log n raised to the power log base ba gives us n squared. So now we're going to compare this value with the function. We know that the function is basically n raised to the power 1. So if we compare this function with n log b by a, so comparing the function and n raised to the power log b a. So when we will compare this function with this, we see that fn is polynomially lesser than the, or I should write polynomially smaller than n raised to the power log b a. So you can see that the function is polynomially. That means that this whole n square, which is a polynomial, and n raised to the power 1 is basically smaller, will give you a smaller value than n square. So let's suppose the value of n is 2. So 2 is less than 2 square, which is 4. So this is what this line means. So when the value of function is polynomially smaller than this value, then we know that this represents our case 1, where it is said that the function is having big O of n log base ba, minus epsilon. So minus epsilon basically means slightly smaller than, polynomially smaller than log b by a. So we are going to apply case 1. So we know that this condition is true. So now the runtime of this type of algorithm will be big O of n log b by a. So the runtime of such type of recurrence relation will be big O of n log base ba. And we have already calculated the value of n log base ba, and the value is n square. So the runtime complexity or the time complexity of a recurrence of this equation will be big O of n square. So let's take one more example. And we will see how we will see in this example too how we can calculate the time complexity or the runtime of this recurrence relation. So let's suppose I'm given a recurrence relation like this, n divided by 2 plus n square. Now I will have to compare this whole equation with equation number 1. And when we will compare it, we will get the value of a as 2 and b is also equals to 2, and the value of function is n square. So now what we are going to do is we are going to follow the step 1, which is a very simple step. You will just have to calculate n log base ba. So it will give us the value n log base 2, which is basically 1. So it will be equal to n. So log base 2 gives us 1, because 2 raised to the power 1 is equals to 2. So you can see that now the value of n log b by a will be equal to 1, and the function that we given to us is equals to n square. So now we know that the function is polynomially greater than n raised to the power log b by a, which is basically n, as you can see here. So now the function is polynomially greater than n log b by a. So in such type of situation, we know that we are going to apply case number 3, because you can see that in this case it is mentioned that n log base ba plus epsilon. Plus epsilon means polynomially greater than this value. So then we will get the time complexity of such algorithm as big O of the function itself. So this will give us big O of the function itself, and we know that the function is already n square. So now we have applied both the cases. So now let's also take one more example so that we will get a good practice of it. This one is the last example that I'm taking. So let's suppose we have a recurrence or a recursive algorithm, and it represents this equation that I'm writing here, plus n cube by log n. So now you can see that if we compare this equation with equation number 1, we will get a equals 8, b equals 2, and the function is basically n cube upon log n. So now we are going to find out the value of n raised to the power log base ba, which is n log base 8. So it gives us the value of n cube. So when you have got this value n cube, you can see that the value of n cube is greater than n cube by log n. We know that the value of n, if we will divide anything from this value n cube by log n, we are dividing it by log n, so this will be smaller than the n cube. So basically from this part I can infer that the value of the function is lesser than n log base ba. So in such type of if you will get this inequality, you can see that uh, this actually refers to our case number 1. So case number 1 says you will have to write it t raised to the power n o big O of log n raised to the power log base ba. So the runtime complexity of this type of algorithm will give us big O of log base ba n raised to the power, which is equal to n cube. So this will be the runtime complexity of this equation.